Hi there, we're back with Blitzer's Introductory and Intermediate Algebra for college students. We're on section 12.2. I am Professor Shannon Gracie from Miracosta College. Today we'll be covering logarithmic functions. So listed up there is all the good stuff we're going to be learning today. Let's get started with a warm-up here. Graphing y equals 2 to the x. So pause the movie and give this one a try. All right, let's see how you did. So we've got x, y is equal to 2 raised to the x, and then our ordered pairs will be in the form of x comma y. So x is, we can give it values, let's say -2, -1, 0, 1, and 2. So when I plug in -2 for x, we'll get y equals 2 raised to the -2, which is 1 over 2 squared, which is 1/4. So we get the ordered pair -2, 1/4. When y is equal to -1, or when x is equal to -1, we get y equal to raised to the -1, which is 1 over 2 to the 1, which is 1/2. So we'll have the ordered pair -1, 1/2. And then when x is 0, we get y is 2 to the 0, which is 1. So we get the ordered pair 0, 1. Y is 2 to the 1, which is 2. So we'll get 1, 2. And y is 2 squared, which is 4. So we'll get 2, 4. So what we'll just do is standard scale. And don't forget to name your x's. So here we are. So -2 1/4 is about here. -1/2 about here. 0, 1. And then 1, 2, 2, 4. And if you wanted to get one other ordered pair, you'd be at 3, 8. And there's our nice exponential graph. How'd you do? Awesome. All right, so moving right along. We now move into the definition of the logarithmic function. So basically, the exponential and logarithmic functions are inverses of each other when they match up. So for x greater than 0 and b greater than 0 and b not equal to 1, so those are the same restrictions we had on our exponential, y equal to log base b at x is equivalent to b to the y equals x. So a logarithm is an exponent, right? So that's the key. A logarithm is an exponent. So see how over here you have y is equal to this log function, and look in the exponential form, y from here is the exponent. So a logarithm, if you have a logarithm on one side and something else on the other, that something else is the exponent. So the function f at x equal to log base b at x is the logarithmic function with base b. So in the first part, all we want to do is we want to change each of these equations into its equivalent exponential form. So the base is good, 4. So 4, actually let's write it like this. This one literally means 4, so the base gets bigger. A logarithm is an exponent, so good. The 2 is the exponent, 4 squared equal to x. All right? What about this guy? This one means, good, 3 raised to the, which is the logarithm this time? Or which is the exponent this time? Good. Y is equal to 81. All right. So next up, write each equation in its equivalent logarithmic form. So this one means, help me out here. Good, I've got to write log. My base is e. Good. And then I know that a logarithm is an exponent, so after the equal sign I'm going to put y, and what's left? Awesome, 9. And this guy, you give this one a try. You start out with log, remember? And then you figure out what the base and the exponent is. Good, so log, the base is b. The exponent will come after the equal sign, so that's 4. And what's left? 16. So let's see what we have over here. Evaluate. Now, on this one, I apologize. I had a bit of a typo. We're going to edit these problems, okay? So we're going to scribble both of these out, and we're going to change them. I had these more in the format of solving logarithmic equations, and we're not ready for that yet. So the new problem will be log base 5 at 25, and then over here we're going to have log base 81, 9. So now the way to think about these, you can change them to exponential form, but let's look at another way to think about these. Literally, this means the power to which we raise 5 to get 25 is blank. So what's the blank? Good. 2. So this is equal to 2. And then over here, the power to which we raised 81 to get 9 is, good, 1/2. Right, so that's going to equal to 1/2. Because if you square root 81, you get 9. All right, so here we go. Here's some basic properties, basic logarithm properties involving 1. So the first one, the power to which we raise b to get b is, good, anything to the first power is itself. So the power to which I raise b to get b is 1. And then the power to which I raise b to get 1 has to be, so anything raised to the, good, 0 is 1. So you get 0 here. Now, inverse properties of logarithms. So for b greater than 0 and b not equal to 1, log base b evaluated at b to the x. So when you're evaluating a logarithmic equation at an exponential or logarithmic expression at an exponential expression with the same base, you just get whatever was in the power of that exponent. So you just get x. same thing, if you're evaluating an exponential expression at a logarithmic expression with the same base, you get what's inside that log. So here we go. And this is because they're inverses of each other. So log base 6 at 6 will be, the power to which I raise 6 to get 6 is 1. Part B, log base 12 at 12 to the 4th. So the base of the log is 12. The base of the exponential is 12. So what are we going to get? Great, that 4 there. All right, log base 9, 1. So the power to which I raise 9 to get 1 is 0. Good. And lastly, the 7 raised to the log base 7, 24 is going to be what's in the log, 24, because the log has the same base as the exponential. So those were a little tricky. So these guys have the same base. That's why we got the 4, and these guys have the same base. Okay, so here we go. There's a couple of ways a person could go about, doing this graph. I suppose it just depends on how comfortable you are graphing the exponentials. You could graph the exponential and then, reflect across the line y equals x to get the graph of this, or you could just graph it directly. All right, so I'm going to do it. I'm just going to graph it directly, and then, but if you need to graph, g of x equals 3 raised to the x and reflect this across the line y equals x to get the end graph, that's okay. So let's see. I have x. I have f at x is equal to log base 3 at x, which remember means the power to which we raise 3 to get x. And then our ordered pairs will be in the form of x comma f at x. Okay, so I'm going to go ahead and start with the resulting x being a fraction. I'm going to have it be a fraction that is, powers of 3 so that it works out nicely. So I'm going to start with 1/9. So f evaluated at 1/9 is log base 3 1/9, which means the power to which we raise 3 to get 1/9 is, very good, -2. So we'll get the ordered pair 1/9 -2. And then we'll do 1/3. So f at 1/3 is equal to the power, that makes the power to which we raise 3 to get 1/3, and that is -1, because 3 to the -1 equals 1/3. So we'll get the ordered pair 1/3 -1. And then if I do a 1, so f at 1 equals log base 3 1. So that's the power to which we raise 3 to get 1, and that is 0. So we get the ordered pair 1 0. And then 3, f at 3 equals log base 3 3. So that's the power to which we raise 3 to get 3 is 1. So we'll get 3 1. And then lastly we can do 9. F at 9 is log base 3 9. So the power to which we raise 3 to get 9 is 2. So we get 9 2. And then remember, this is the reflection of the graph y equals 3 to the x across the line y equals x. So you can also do it that way. So here we go. This is x and f at x. All right, so we had ordered pair 1/9, -2, so that's going to be really close to this y-axis. Actually, closer than that, I think. And then 1/3, -1 will be here about. And then 1, 0. And then 1, 2, 3, 1. And then 9, 2. So the graph looks something like that. Okay. So the domain goes from where to where? Good, it's going from 0, not including it, just gets really close to 0 on to infinity. And the range, even though it looks kind of like it levels out, it doesn't. It keeps increasing. So the range happens to be all real numbers. Okay. So here we go. Characteristics of logarithmic functions of the form f at x equals log base b x. So the domain is all positive real numbers, so 0 to infinity, not including 0. The range, all real numbers. Oh. The graphs of all logarithmic functions of the form f of x equals log base b x pass through the point 1, 0 because f at 1 is equal to log base b1, which is 0. I don't need that. The x-intercept, therefore, is 1, 0. There is no y-intercept. If b is greater than 1, the graph is going to go up to the right. And is an increasing function. If b is between 0 and 1, the graph is going to go down to the right and is a decreasing function. So the graph of f of x equals log base b of x approaches but does not touch the y-axis. The line x equals 0 is a vertical asymptote. Okay, so here's, just a little picture of what's going on those situations. So when b is greater than 0, you're going to get a graph that looks something like this. It's going to go through 1, 0. And then if b is between 0 and 1, you're going to still have a point at 1, 0. But the graph is going to go like this. Something like that. All right. find the domain. So we know the domain is all positive real numbers. So here we set x minus 4 greater than 0. X has to be greater than 4. So in interval notation, we're going to go 4 to infinity. You guys try part B. All right, let's see how you did. You set 1 minus x greater than 0, negative x greater than, greater than negative 1. So x would be less than 1. So minus infinity to 1 would be our domain. So now we get into common logarithms. The logarithmic function with base 10 is called the common logarithmic function. The function f at x equal to log base 10x is usually just written or expressed as f of x equals log x. So if you don't see a base and you see it written as log, L-O-G, you assume a base of 10. So a calculator with a log key can be used to evaluate common logarithms. So here we go. This one is equivalent to log base 10 at 1,000. Now, so the power to which you raise 10 to get 1,000 is? Good, 3. Now, on scientific calculators, a lot of times you're either going to do, most scientific calculators, you would do the 1,000, then you would hit the log key and then enter, and you would get 3. If you if that one doesn't work, then try the log key first and then 1,000 and then enter and see how it works. All right, so this guy, this means log base 10 at 100th. And so the power to which we raise 10 to get 100th is, good, -2. Properties of common logs, they're going to be very similar. Log 1, that means the power to which we raise 10 to get 1 is 0. Log 10, the power to which we raise 10 to get 10 is 1. And these, again, you're evaluating the common log at a base of 10. You get what's in the exponent. And then if you're evaluating an exponential expression with base 10 at a common log, you get what's in the log. Okay, so here, this guy, remember, would be log base 10 of 10 cubed, so you just get that power. This guy would be 10 evaluated at 10 raised to log base 10 at 7. So you're just going to get what's in the log. That's because, again, the bases match. Now, natural logarithms are used quite a bit in higher math. The logarithmic function with base e is called the natural logarithmic function. The function f at x equal to log base e, x is usually expressed as f of x equals natural log at x. So a calculator with a natural log key can be used to evaluate common logarithms. Again, you'll have to work with your calculator to see if you need to press the ln key first before the value or after. Okay, so the properties of the natural logarithm are, going to be similar. Here that we have the natural log 1, the power to which we raise e to get 1 is, good, 0. Over here, the power to which we raise e to get e is 1. And then we're evaluating the natural log at the natural exponential function, so we'll just get what's in the power. And over here we're evaluating the natural exponential at the natural log, so we'll get what's in the log. So here we go. This guy is equivalent to natural log at e to the negative 6. So we're evaluating the natural log at the natural exponential. So we just get negative 6. We get what's in the power. And here, e raised to the natural log at 300 is just going to be 300 because, again, we are evaluating the natural exponential at the natural log, so we get what's in the log. Okay, so here we go. Example 10. Find the domain of natural log at x minus 4 quantity squared. So this one's going to be a little different because we're squaring the quantity that's in the log. So we just got to think to ourselves, okay, x minus 4, the quantity squared has to be greater than 0. So for this one, anything squared is going to be positive, so we just can't get something that'll yield a result of 0. So we have x minus, so basically, do you see that x cannot equal to 4 because that is the value that would yield a result of 0. So in interval notation, that is minus infinity to 4 union 4 to infinity. All right. So that wraps up the lecture for today. We'll be hitting 12.3 next, which are properties of logarithms. So have a great day.